So I cannot emphasize enough regarding the boundary condition. Okay, the boundary condition is so important. Okay, without the boundary condition, like I showed you all before, the entire expression will go wrong. Okay. Now,
Eugene,
yes.
when we have our final exam, will we have a question where we have to do an integration like that as part of the question?
Yes. Then why do you think I'm teaching you, cheeky sort? Okay, you have to. Okay. Now, Christian, definitely. Okay, Christian, are you okay? It's not that bad, right?
Yeah, it's not too bad. I'll just need to practice it more.
Yeah, but the integration is not like what you've been taught in your math course. Yes or no? It's so much easier. Am I right? I think so, right? You just the way to do this is you need plenty of sleep. Okay, and yeah, not just sleep. Okay, you have to prepare for the course. Now, one thing I'm thinking about how the solution manual will confuse you. Okay, now regarding this part, okay, there is different ways to get your moment. Yes or no? Over here, I show you using the integration method, right? Pure integration. But if you want to use positive shear and positive bending moment, your answer should be the same. Okay. If your answer is wrong, then different, then there's something wrong. Okay. So I'm going to I'm going to show you. I'm going to apply. Okay. How to find moment equation again. Okay. So we are going to look into moment equation. Okay. I just want to show in case some of you don't find it comfortable to use this expression over here, right? You want to use positive shear, positive bending moment. You can. The answer should be the same. Okay, so I will show you it is the same. Okay, so apply. Okay, option 2. Yeah, I'm going to show you option number 2 to apply positive shear. And positive bending moment to find the moment equation. Okay, so now same thing, not same thing. There's an extra step over here. Okay, you have to find the reaction at point A. Okay, you don't need to find the reaction at point B. You don't need, because our analysis is going from left to right. Okay, we're going to do analysis from left to right. So point B is not important, not important, but we want to find AY, right? So we're going to find. Okay, so we have a load like this. We're going to find AY, right? So to find AY, okay, you have to find the equation, okay, equation of the distributed load. Now I'm going to do integration all the way now. Okay, so the function is omega as the function of x, so this is equal to omega naught over L, right? All right, then to find the equivalent load, omega equivalent, right? So it's going to be equal to we're going to integrate. Oh, I'm missing the x. You're going to integrate 0 to x. Okay, so this is omega naught x squared. Oh, come on, Eugene. I thought towards the noon time I should be more awake. Econ opposite, right? So this is equal to omega naught x squared over 2L, right? So equation number 1, equation number 2. Equation number 2 is your equation of your distributed load. Right. So now if we want to find what is our equivalent load, when x is equal to L, so it's equal to what? Omega naught L squared over what? 2L. So this is so equal to omega naught L over 2. Okay. This is using the function, and I'll encourage you to use the function. Okay. I don't want you, I know if I'm going to consider this whole thing as L, I know you guys will tell me, Eugene, this is half base. Okay. Or omega naught L. By observation, area of a triangle, it is exactly the same when you use the integration method. Okay. So now you know, right? Are you okay? I think you are okay. Okay. So now you find your reaction. Again, I want to emphasize you only need to find AY. Because we are going to do from right to left, yes or no? Now we know that over here, this is omega naught L over 2. From the distance from here to here is L over 3. And this is your point B, right? So you are going to do summation about moment. In the Z direction at point B is equal to 0, right? So the distance from here to here is L, okay? So you do that. So we're going to take moment at point B, right? So you have minus AYL, right? Plus by omega naught L over 2 multiplied by L over 3. So the whole thing is equal to 0. So minus AYL is equal to minus omega naught L squared over 6. So AY is equal to omega naught L over 6. Yeah, you get rid of the, do I get rid of the, yes, okay. So from here, you just need to do the moment equation. You don't need to do the shear force equation for this case, because we want to achieve what? We want to find moment, okay? We want to get to the moment, okay? So now we know that AY is equal to omega naught L over 6. This is a function of X. Over here, immediately you plug in your equation where it's equal to omega naught X squared over 2L. Over here to here is X over 3. So you only need to know your moment is in that direction. Okay. So we are going to use, we're going to find moment. Okay. So again, anti-clockwise is positive summation of moment in the Z direction as a function of X is equal to 0. Okay. So you take a moment over there. So this expression, so the first one is the omega naught L over X or L over 6. So it's going to be in the clockwise. So it's minus omega naught L over 6x, right? Then the other one is plus omega naught X squared over 2L multiplied by X over 3, right? And then this expression, then plus by omega as a function of X, the whole thing is equal to 0. So M as a function of X is equal to minus omega naught X cubed over 6L, right? Bring over plus by omega naught L over 6x. Okay. Am I right? I think so. I need to check. So from here, right, you realize that this expression and this expression are the same. And then you apply elastic curve. Okay. But you can see for yourself, right, how much more steps that you have to do, right? But the advantage of using positive shear and positive bending moment is what? Can anyone tell me, please? What is the advantage? Hello? Anyone, please? You don't need to know boundary condition. Okay. Okay, I think I made a mistake. Someone telling me that my last expression is wrong. Ankit Joshi, isn't the last term? When you say the last term, did I make mistakes down here? C3,
Omega 0.
huh?
It's about omega 0 instead of omega, I think.
Where is omega 0?
On those equation 5 and 6, like the final form where we substituted C3
C3. Where is
minus
it?
7 upon 360 omega 0 L cube, I think that's what he's
Okay,
saying.
so it's the omega, not is okay. Thank you so much. L3. Thank you. No, this is first one is L4. L3. Okay. So I just put thank you for telling me that you're right. So this is L3 and this is L3X. Okay. Ankit, is that the one for EIX? He just put the last term. Okay, I think you're right. Or is that Ankit speaking? No, I think that's Shintel, right? Okay. Right.
Professor,
Yes.
when we have a multiple movement equations in a like single beam, when there is a
Yes.
load change, so we will do this whole process, apply elastic curve at each equation.
So what I've just shown you is a continuous function, right? It's
Yes.
continuous, right? So if you have a load, right? So let's say it's not continuous. It is like this, right? Like this, right? Point A, point B, point C, point D, right? Now you have to have functions that have a limit between A to B, B to C, point C, and C to D. Remember that? So you are forming function. Remember, we have function that we have function where we have section, right? We form functions in section A to B, B. Am I right? Then we form our V as a function of X and M as a function of what? X. So each of them have different function. Am I right? You
Yes.
have to use, let's say you want to find A to B, you have to use M of X in this function over here, right? And then you carry out your elastic curve. Does that make sense?
Okay. Thank you.
Make sense? Yes or no? You understand what I mean, right? Okay. Okay. The next one, we are going to the last example that I'm going to do. Okay. Is the example of statically indeterminate structure. Okay. Example number 3. Okay. Is statically indeterminate. Okay. Okay. So we are going to apply statically indeterminate structures over here. So we are going to. So what do I mean by statically indeterminate? So you have a beam, right? Then you have a cantilever. Okay, you have a cantilever over here. Then we have a triangular load. Okay, and then this triangular load again at the peak is omega naught. You guys have say, hey, we seen this before. Okay, you guys say we have seen this before. Yes, you have seen this before. Okay, so now, so this is our point A, point B. At point B, I have a support, a roller support. Sorry. So this structure, so the question is find the reaction at point B. right? And we know that point B is redundant, right? You don't need it to be there, but the structure can still support itself. But we cannot use statics to solve it. Okay, we can't do it. Why we cannot use statics